Okay, I think we'll get started. So I hope you've had a chance to practice with the strong acid, strong base titration. Today we're going to talk about a weak acid with a strong base. So now we will have to do some equilibrium calculations with ice charts, but we've been comfortable with that, and now we've gotten comfortable with this idea of a titration with the strong acid, strong base. So let's just put those two things together. So let's say we wanted to titrate 25 milliliters of 0.1 molar niacin, which is a weak acid, a Ka of 1.4 times 10 to the minus 5. We're going to titrate that with 0.1 molar NaOH with this strong base. In principle, you could do a weak acid, weak base, but you usually have the choice of somewhere along the way in the reactions, and that would be a rather poor choice when you have an option to use a strong base. So we'll be talking about weak and strong here as a primary as we go through here. This is going to be a weak monoprotic acid. The next lecture we'll do a weak polyprotic acid. And that will be the types of acid-base reactions that we'll be doing titrations with. Okay, so let's calculate as before. So we can calculate the total moles of niacin, and we're going to add Y milliliters of NaOH. So we're going to get 0.1 times Y moles of NaOH added. We're going to do this before the equivalence point, so that means whatever this is, this number is bigger than that, and so we have niacin left over. So we can figure out how much the concentration of niacin left over, because we will take the base to react 1-to-1 with the niacin, because it's a monoprotic acid. And of course, sodium hydroxide is a monoprotic base. So we can take number of moles and divide by the total volume here to get the concentration of the niacin. Well, what was made when it reacts with the sodium hydroxide is the conjugate base to the niacin, which we'll call Nia minus. So this is deprotonated niacin. And how much did it make? It made exactly the amount of moles of sodium hydroxide that we put in. And so that gives us a concentration of the conjugate base. That's that. But that's not where it is. So if we were to stop the titration there, that's not the equilibrium amounts. What we've done is we've slammed everything over, like we've done in the past, with the base, and then we're going to let this come back to equilibrium. So we simply plug in these as our initial values, and then we calculate with an ice chart our change. And we don't get a single answer here, but we get a formula based on how many liters of the sodium hydroxide we've added. So it would be very quick to then put, say, 10 mils, put in 0.01 milliliters, or liters, and solve for X. And when you solve for X, that will give us the H plus concentration. And so that will give us our pH. So the pH, the X concentration, X will equal the H plus concentration. And then we would just take the negative log of that to get the pH. Now let's get to the equivalence point. So here's when we've added exactly the right amount of base so that all of the base has reacted with the niacin, no limiting reagent. So we slam that all the way over, and we have only conjugate base present. And so we can figure out that concentration. It's going to be the total number of moles of niacin that we started with, all converted. And now we have to go back to the details of our problem. We've got the same concentration, so we know that this will occur at 25 mils. Now, we may have a different concentration, and then we would have to figure out how many milliliters of sodium hydroxide we've added. But we, in this case, we are now at 50 mils. And so that gives us a 0.05 molarity solution of the conjugate base. Then we have the conjugate base reaction with its attendant Kb, which we can get from the Ka by taking Kw over Ka, because this is the conjugate base of the niacin acid. Okay, so now we need to figure out what is the pH at the equivalence point. It's not 7. It's tempting to say 7, but it isn't, because we always have that conjugate base have to come back to equilibrium. So we have 0.05, 0, 0, set up our ice chart, solve for x. X is going to be the concentration of OH minus. And we get, in this case, we get 6 times 10 to the minus 6. And if we take the 14 minus the log of that, because this will be the POH, then we get 8.78. And as we might expect, we're adding a strong base to a weak acid, so the equivalence point is going to be shifted from 7 towards the basic end. If this was flipped around and we were titrating a weak base with a strong acid, we would expect the equivalence point to be at a slightly more acidic pH. Okay, well, we have one more part of this, and that's after the titration. But this becomes easy. This becomes like last time. The sodium hydroxide is in excess. We say that it has completely reacted with the niacin. So we wipe out this many moles of however much we put in. And we put in 0.1 times Y milliliters. And so we'll have 0.1 times Y minus this, and this number is going to be, this number here is always going to be bigger than this because we're after the equivalence point. So we can get the concentration, just take that number of moles by by the 25 mils right here in the form of liters plus Y. And then we would take the negative log of that to get the POH, subtract that from 14, and we would get a pH somewhere above the 8.78, start to become acidic. All right, let's capture this in the form of a titration curve like we did last time. Very similar, except that we're going to start at a higher pH because we're not a strong acid. And we're going to have a slight slope up until we get close to the equivalence point. And then we'll zip through the equivalence point. And now we've calculated here where our equivalence point is and what the pH at that equivalence point is. So the equivalence point is at 25 milliliters of OH added, and the pH is 8.78. Then beyond that, we climb up to a high pH, peaking out at a pH of 13, which is what this would be if it was all alone. So when we're in big excess of our titrant, then we reach pH 13. All right, so this is a weak monoprotic acid with a strong base. The next one we'll do is a polyprotic acid.